It's Friday night. Everyone is hungry, and you've just made the mistake of volunteering to handle the pizza order for the group. The requests are coming in fast. Sarah is vegan, Mark hates mushrooms, and Dave insists he'll only eat a meat lover's pie. Resolving this argument without leaving someone hungry is a logic puzzle that mirrors the core problems of computer science. This specific branch of math is called discrete mathematics. It deals with distinct, separate values, like individual people and their strict yes or no preferences. By solving this dinner order, you're using the same logic that modern software uses to organize data and make complex decisions. To find a solution, we first need to organize the friends by their specific needs, using a concept called set theory. A set is a collection of things that share a specific rule. We'll start by creating our first set for the vegans in the group. Now we create a second set for the friends who require gluten-free options. When someone has both restrictions, they sit in the middle, where the two circles overlap. This is the intersection, a specific subgroup that must satisfy both rules at once. If we want to see everyone in the group who has any dietary restriction at all, we look at both circles combined. This total area is called the union. Set theory gives us a visual map to take chaotic, conflicting data and sort it into clear, manageable categories. Now that we've grouped the people, we have to create the strict rules needed to select the actual pizza. In programming, these rules are built using three foundational words: and, or, and not. We can start with a not rule to protect the vegetarians. The order must not contain meat. Then we use an and rule for our most restricted eaters. The crust must be gluten-free, and the toppings must be vegan. These logical operators act as filters. They replace vague human preferences with concrete, binary requirements. To test these rules against the pizza menu, we use a tool called a truth table. A truth table evaluates every possible combination of true and false. It's a way to ensure we haven't missed any potential outcome. We'll label our columns with our requirements: meatless and gluten-free. If a pizza is meatless but contains gluten, the final result is false. If it's gluten-free but covered in ham, the result is also false. The only successful outcome is when both rules are true. When we find a pizza that is meatless and gluten-free, we have our answer. This strict table removes human error. It exhaustively proves which specific choice satisfies every single parameter we set. This isn't just a helpful way to order a group dinner. It is the physical architecture of modern computing. Inside a microchip, these true and false results are represented by physical pulses of electricity. A high voltage represents a true, and a low voltage represents a false. Computers use these electrical true and false checklists for high-stakes tasks. An autopilot system constantly checks rules. If the altitude is below a certain limit and the landing gear is down, then trigger the landing sequence. Your banking app does the same, checking if your password is correct and if your fingerprint matches. If one of those physical electrical signals is false, the vault stays locked. At their core, computers are simply machines that process these basic logic grids millions of times per second. So when you're standing in your kitchen, trying to find a pizza that Sarah, Mark, and Dave can all enjoy, take a breath. Discrete math is often presented as a wall of abstract symbols, but those symbols describe how we naturally organize our lives. When you balance a complex group decision, you are manually executing the same logic that runs the digital world. The distance between a computer engineer and a person coordinating a group dinner is much smaller than it looks. You're both just using the same rules to turn chaos into a solution.